Hello everybody and welcome to another video. In today's video, I will be giving you an introduction on the architecture and the concept of the C REPL. Now, let's back up a little bit and talk about what is a REPL. The REPL is the interactive shell which executes your code per line. So, if I say something like this, it will be line by line at runtime. And this is really difficult to accomplish in C, since C is a it's a compiled language. How do you even grasp executing the line by line C, where you see behind the scenes in this Python interactive shell, this piece of code gets turned into bytecode and then we get to execute it. That's why there is eval function, but eval function doesn't exist, and it stands for evaluate your code. But it doesn't exist for languages like C, C++, etc. All the compiled static languages. So it really gets challenging to even try to do something like that. And I've seen a lot of implementations online of the C REPL where they are flushing the std out so that they don't execute the previous code. What do I mean by that? So they built a program that it's gonna take your line and put it into the main file, and you'll do A, and then on the next time around you will do print A. And next time around, if you want to print it again, it will rerun the entire main because it just set it up. Even if you somehow lexically determine that you will cancel out all of the expressions in your main function the next time around, the next time you evaluate your code via your own implementation of eval, the address of A will be different because we reran our code. We recompiled and reran our code, our program. So the main issue about making a C REPL is having to preserve the state of your currently running program. How can we possibly do that? My approach, and I thought about this long and hard, my approach would be to just compile and link my runtime dynamic libraries and do DL open, and then I can do DL sum. So essentially, each time I'm creating a variable, I'm going to create a new DLL file with only one variable. So I'm only doing one file per variable. So each time I'm creating a new, and we can get away with this because GCC compiler is pretty fast compared to G++, and when you're executing your code in real time, you cannot notice that there is a whole lot happening behind the scenes. It's all pretty fast. But what we need to always keep tabs on the compile time in this case. But essentially, because DL open and DL sum, they don't make me get out of my program, which means that I'm using this technique for placing all the functions and all the symbols into a single unity that can be shared by multiple processes at runtime. And now, because the state of a dynamically loaded library, for example, DL_SUM and DL_OPEN, they are kept as long as the handle returned is active. And what I mean by handle is the handle returned by DL_OPEN. So it is active until I close it. So I can do this. But then what you need to do, because all of this stuff is really complicated to pull off, you need to transform or translate your code at the front end. So you need to take these at the front end of the compiler. So you need to take this, turn them into DL_OPEN, DL_SUM, and run your eval. And here's how I'm able to accomplish that. If I look at my main program that is going to do this for me, it looks something like this, right? So if I take my main program, I'm initializing the context, which and I'm trying to use heap as much as possible in this case, because there are a lot of edge cases when it comes to opening your DL handle and having to call a function where everything, because all of the handles, they have their own data segment, and if you use something from the data segment, such as, I don't know, const character pointer, and you try to use it when you close it, now we are going to result in undefined behavior. So I'm trying to use heap as much as possible, for example, the context. So my main function doesn't result in undefined behavior. So I first initialize my context, and my context will be a collection of what I call runtime entries. And runtime entry is essentially my variable that I defined. For example, if I've defined a variable like this, int a equals to 1, I will first create its shared dynamic library, which will be like this, because I need to load everything into my current program address space and keep it that way until we close it, until we do DL close on all of the DLLs. So I have to preserve the state of my program. And then what I do a translation of that DL_SUM and DL_OPEN, and then I am resolving it at runtime with DL_SUM, and I'm placing it in the variables. So next time, and I'm pushing it onto the runtime entries because they need to be somewhere, and I'm running this for my eval function handler, since my main program needs to keep running. And you may be wondering, where is our main program? Well, I thought about using something like pexpect, where I would create a bridge to communicate with my C program that will have the DL handle like this and run it in a loop. But then, when it comes to these libraries, it's always better to cut out all of the dependencies that you're using in pexpect. And pexpect is a library that communicates for communication between two programs if one program is like has like scanf or is waiting for input. But I even find this usage a little bit confusing for someone who isn't familiar with the library itself, and I think this library is a bit of overkill in any project. Unless you really have to use it, you gotta use it. But our main program is the Python itself. If I look at this diagram, Python is implemented in C. And Python, when it runs, it's actually a C program. So what I did, my main program of running the C REPL is this. I'm loading the library, and I can treat this code as a C program because I'm directly loading the library from Python. And since Python is the C program behind the scenes, we can have this to work. And that's where my C REPL runs or revolves around. If I take a look at this code here, where's the C REPL? 1 second. So the C REPL revolves around the Python program where I can run my evaluate function at runtime. So that's how we cut out the pexpect library, and that's how we are able to run this. So now let's verify that all of our variables are persistent. So the persistence is the key with the REPL. So I'm just gonna print out the address of my A, and it is this. Now if I try that again, I didn't implement the read line, but if I try that again, it's the same variable. Now we have our program persistent. And the way that this works, now if we look at our main eval file, where we run our function, is that we extracted the cast. Why do we extract the cast? In order to dereference our variable. That is because all of the symbols in the dynamic library, they're void pointers. So we have to find a way to extract the cast, and there's a lot of code here that I've built that would accomplish that. For example, it's here. I can get the type as PTR, and I'll be walking you through this in the next bunch of videos. How am I exactly doing this? But that's the concept in order to keep our program persistent and not have any weird stuff that I talked about in the beginning of the video. This needs to be completed at runtime with without our program freezing or rerunning again. So yeah, I can also define a function. So what happens is that I break down C parser or parsing output, and I replace all the IDs with the exact lookups that I need to make in terms of DL sum. So when I do printf, as you can see here, that's where my my A is. If I define B, oh, now I need to do it again. So A and B, I need to add the functionality where you don't have to necessarily add the semicolon. So now what's happened, because I appended the B, it will be at 1 index. So when I try to print it out, B is 2, and it will be at 1 index. That's because how it is defined at the Python level, so that we can look it up and just write our generated code onto the DLL file, recompile it, and run it again. And we are able to do that because each time we're calling eval, we are closing the main eval. If we take a look at that code, which is the eval function, I'm unloading all of my DLL references, and that's it. Now I can rerun my function from the ground up, and nothing will be cached or saved or whatever. So that's how I'm able to accomplish that. So if I go back to our diagram here, this is our Python program that we are treating as a C program. Then we have the C source. We perform the transformation using the PyC parser, and I had to fork my own version of this in order to have this to work. And I had to do all sorts of weird stuff like changing the grammar rules. For example, I needed to change the grammar rules because at the top C code level, you cannot call a function. You cannot have any expression. Nothing. You can only have declarations such as structs and function definitions. So I had to modify the grammar rules of the parser in order for us to have a working REPL. And then what we do there is, once we do our transformations, we output the code onto C and we compile it and link it here, or actually here, first onto the of our library, and then we compile the main eval. Main eval is just the evaluate function, but because we need to store our persistent variables at runtime, we need to open each DLL file at runtime, because we have to store them in our current program space address or virtual space. That's why we use LD open, LD sum. And I've written a lot of unit tests to verify that all of these are persistent in the current virtual memory space for our running program. And yeah, now we can talk to our context to store all of those on heap so that we can later refer to it if we want to use them. And once we do printf or something like that, so once we do a printf, then we are essentially just reusing that B variable, and it's located at one index. And I'm using indexed like accesses because it's zero runtime cost. And because my subprogram is in Python, I can build a hash table that's going to say, okay, your variable is at zero index, as we can see here. My runtime entry where my A variable is at O index and my B variable is at 1 index. So that's how we pull it off effectively. So that's when we get to use our runtime entry, we have to store it on heap. So now let's talk about defining a function. If I define a function that goes like this, and this is really experimental, very early project of mine that's not yet open source, but it will be open source any day now. If you're interested and you want to see the source code before I open source it, let me know in the comments below. So now when I define a function, let me just define a different one. Let me define f1 or ff. So now I've created another DLL file that will be library ff, and that's where my function resides and persists, preserves rather. So if I take a look at my main eval, my main eval makes sure to resolve that function at runtime and do a DL sum on it. So now that we stored ff with the respective casts, I can now call my function ff123. Now I can see the output of my function ff123. Now if I take a look at my, okay, we stored our runtime entry, now we get to access it, it is at index 3. We are doing the cast, we extracted the cast because, as I've said, DL sums and DL opens, they're all void. They require a cast at runtime. And then we go back to our main eval function. That's run by Python. And I said Python is a C program essentially. That's why we're able to accomplish this with C types here in the code. So my class is called C interpreter because we are essentially interpreting the code. We are compiling it and we are running it at runtime without our main program closing. So you can essentially say that this is an interpreter behind the scenes. So when I'm testing the interpreter, I'm creating my instance and then I'm running my interpret function. And my interpreter will do all the work that needs to be done. There's a lot of if-else's. If there's a declaration, we're gonna go with one logic. If there's a function definition, we're going with another logic, and so on and so forth. So that's the front-end transformations we need to extract and make as a middleware in order to run our C code. And this is not noticeable because the machine's gotten really better over the past few decades, or the past decade rather, where we don't see that there's a lot of stuff happening behind the scenes. So if I run my it's instant. If I run my my line of code, it's instantaneous. So and we can see that our the main eval handle is different each time. That's because we closed the previous one in order to open up a new runtime function where we get to reuse our context, and our context will always stay immutable, and it will always be persistent in memory, since our main program is running at the Python level. All right, that's a quick introduction to the C REPL. I hope you enjoyed watching, and until next time, take care.